Now, let us start the next things. Come to the convex set. Earlier we have talked about the basis, dimension and the spanning set. You have a set X, we say that the set X is a convex set if we can find out the 2 points which belongs to X, and if I join these 2 points x1, x2, the line segment whatever you are obtaining will also lie in the set. That means, any point you take on the line segment, that point also should belongs to X. Mathematically, if I have to say, then I will tell that if x1, x2 belongs to X, then if I can find out this one, lambda 1 x1 plus 1 minus lambda 1 into x2, where lambda 1 lies between 0 to 1, then X must be a member of set X. So, if this is satisfied for any 2 points x1, x2 belongs to X, if X equals lambda 1 x1 plus 1 minus lambda 1 into x2, where lambda 1 lies between 0 and 1, and X must be a member of the set X. For an example, it will be easy if I take any triangle set. This is a convex set. You take any 2 points here, suppose I am taking this and this, if I join this, all the points lies inside this convex set only. Similarly, so this is a convex set. If I take a rectangle like this, then any 2 points you take here, you join them, they will, all the intermediate points will lie inside this rectangle only. So, this will also be convex set. But if I take something like this, suppose I am taking this set, if I take a point here, if I take a point here, if I join, you will see that some of the points are not in the set itself. So, this one is not convex set. So, I hope it is clear that mathematical definition is this one, and geometrically if I have to say, then I will tell like this. From here one more thing comes, that is extreme point. A point X is said to be an extreme point of a convex set if and only, please note this one, if and only if there does not exist any 2 points x1 and x2, where x1 is not equals to x2 in the set. There does not exist any 2 points x1 comma x2, x1 does not belongs to x1 not equals to x2, such that x equals lambda x1 plus 1 minus lambda into x2, where lambda this holds. So, and one point X is an extreme point of a convex set if and only if there does not exist any 2 points x1, x2, where x1 and x2 are not equal and they satisfy this one, that is not a linear combination, convex combination of these two. So, if you see this rectangle here, in this rectangle if I find, let me draw it here, if I take a point x1 here, if I take a point x2 here, this point x1 is an extreme point of this rectangle, or this point x2 is a rectangle, is any 2 points rectangle, because I cannot find any 2 points x1 and x2 or some other 2 points, where if I make the join them, then x1 x2 lies here. But you think this one x3, if I denote this by x4, then x3 is not extreme point, because The reason is that your x3 lies whenever I am joining x1 and x4, x3 is a combination of this x1 and x4. So, x3 is a not an extreme point, whereas these x1 or x4 or x2 or x3 are the extreme points. Already we have done, just I am writing this one to talk about the linear simultaneous equations. Let us think about a set of equations a11 x1 plus a12 x2 plus a1n xn, this is equals b1, a21 x1 plus a22 x2 like this way plus a2n xn, this is equals b2, and a m1 x1 plus a m2 x2 plus a mn xn equals bm. That means you are having n variables and m equations here, n variables x1, x2, xm, and you have the m equations. In matrix notation, I can write it in the form as Ax equals say B, where A is the matrix, I can write down Aij, this is M cross N matrix. Your X will be nothing but the x1, x2 vectors and the transpose of that, and similarly your B will be B1, B2 and Bm to the power transpose. So, in other sense, whenever you are having some equations in matrix notation, always we can write it in the form of Ax equals B. So, because now whatever we are going to talk, this matrix notation will be very useful. Let us come to the basic solution of that system of equations. You have a system of equations Ax equals B with n variables. I have n variables as I discussed earlier, and you have m equations. So, and we are assuming that m is less than n, that is number of equations are less than number of variables, and rank of the matrix A is equals to m. Right. So, since rank of the matrix is equals to m, so therefore, there will exist one matrix B of order, there will be one matrix B of order m cross m, which will be, since rank is m, please note that you may be knowing the definition of the rank. So, it will be non-singular. So, I am getting a matrix B of order m cross m, since I am assuming the rank of the matrix is m. So, I must get one m cross m square matrix, which will be non-singular. So, let A1, A2, Am, these are the linearly independent columns. Since the rank is m, therefore, I must get m linearly independent columns of A. So, A1, A2, Am are linearly independent columns. So, now your Ax equals B can be transformed into a system with m equations and m unknowns, which I am representing by B. So, this is equivalent to a matrix B with m equations and m unknowns, and the remaining n minus m variables what you are having, this n minus m variables will be 0. So, one linearly independent columns are there. So, I have m decision variables in the matrix from where I can obtain the solution of those decision variables, and the remaining variables we will make n minus m matrix. So, this matrix B we call it as the basis matrix. This matrix B is known as the basis matrix. Please note this one. Matrix B, how we are forming? Since the rank is m, rank of the matrix A is m, I must get n linearly independent column vectors, and using those I am forming one matrix B which will be automatically non-singular, and this is known as the basic matrix. Now, these linearly independent columns are there, and corresponding decision variables are known as basic variables. So, in one sense, the variable attached to the linearly independent columns are known as basic variables, and remaining n minus m variables we call it as non-basic variables. So, I have some basic variables, I have some non-basic variables. Basic variables are the variables which are attached to the corresponding to the linearly independent columns, and the remaining variables n minus m variables are known as non-basic variables. So, basically I can say that x b equals x b 1, x b 2, something like this way, x b m. These are the basic variables of the system A x equals b, and the solution can be achieved from here. A x equals b, solution whatever you are obtaining, that will be x b comma 0. So, x b comma 0 is known as the basic solution, S b comma 0 is known as the basic solution of the system of equations A x equals b. So, I am not saying that this is the only solution, this is the solution. I am saying this is a basic solutions. How we are obtaining the basic solution? The basic solution we are obtaining by taking the rank, that is n linearly independent variables from there, and I am forming a matrix B. I am associating the variables which are attached to these linearly independent columns, which I am saying as the basic variables, and all other n minus m variables will be the non-basic variables, and this x b comma 0 is basic solution. So, if you have n variables and m equations, you will have factorial n by factorial m into factorial n minus m basic solutions. So, maximum what you can get, that is by making all the possible combinations, you can obtain factorial n by factorial n into factorial n minus m basic solutions. Just let us take a example, because just we are giving the solution of a system of equations. Let us take the equations like this: x 1 plus x 2 plus x 3, say this is equals 9, 2 x 1 minus 4 x 2 plus 3 x 3, this is equals say 4. So, in matrix notation, if I have to write down, your A will be 1 1 1, 2 minus 4 and 3, your B is 9 and 4, this one B is 9 and 4. If you find the rank of this matrix A, your rank of A will be 2, that I am leaving for you, you just check it, very easy. So, rank of A, and this is equals rank of A B also. Rank of A equals rank of A B if I take, and which is equals to 2. So, number of basic solutions here will be, number of basic solutions will be factorial 3 by this one, factorial 2 into factorial 1, and whose value will be 3. So, what can be the possible basic solutions? from here? I can write down possible basic solutions like this. One can be A1 comma A2. A1 comma A2 means I am telling this column as A1, A2 and A3. So, this will be 1 1 2 minus 4. One can be this. Since the rank is 2, so I have to take 2 linearly independent columns. B2 can be A1 comma A3. B2 will be then A1 A3 means 1 2 1 3, and the third one which you can obtain B3 as A2 A3. These 3 combinations are possible only. This is 1 minus 4 and 1 3. So, if you see I am obtaining these basic solutions B1, B2, B3 like this. Since the rank was 2, so the maximum number of basic solutions I can obtain using the formula factorial n by factorial m into factorial n minus m, this is equals to 3. So, I obtain B1, B2 and B3 like this. So, what can be the basic solutions now? I can write down x B1 equals B1 inverse B. You know what is B1, what is B, you know it. If you calculate, you can obtain this value. This I am leaving for you because of shortage of time. Similarly, your x B2, if you see, it will be B2 inverse into B. The result will be 23 minus 14, and for the third one x B3, this will be equals to B3 inverse B, and this is will be 23 by 7 and 40 by 7. Therefore, we can say that the basic solutions, one is, this is which one? This corresponds to A1, A2. So, A3 will be 0. So, one solution for this problem can be 20 by 3, 7 by 3 and 0. A3 is 0. For this case, it is A1, A3, that is A2 0. So, it will be 23, 0 and minus 14. This is another solution, and the third solution, this is A2 A3, that is A1 is 0. So, this will be 0, 23 by 7 and 40 by 7. So, if you see here what is happening in the process of finding the solution, basically we are trying to find out the basic solution at first. How to find the basic solution? For that we are using the linearly independent columns or the rank. From the rank we can obtain it. Once I am getting the linearly independent columns of the matrix, in that case I am forming a matrix B1, B2, B3 like this, where your B's are combination of these linearly independent columns A1, A2 and A3, and from there we are obtaining the solution. So, this we call, afterwards you will see that this is an initial solution, and from this initial solution we have to improve it and we have to obtain the optimum solutions. So, now let us come to the original thing, that is formulation of linear programming problem. I am not writing the full form. In the linear programming problem, basically I have to take certain decision subject to certain constraints whatever we are having. Suppose I want to set up one factory. To set up the factory, I need the manpower, I need the land, I need the technical know-how, I need, there may have certain constraint on my cash flow. So, I have to find out the solution, that what should I do or how much quantity should I produce, which will satisfy my constraints. So, as we have seen in LPP, we can formulate that thing. The decision making problem basically consists of certain steps. First is Just I am writing the steps: identification of the problem. Basically, you have to understand what the problem is, because if your understanding is wrong, then the formulation of the model always will be wrong. So, first I have to identify and I have to understand what the problem is. So, once I have identified, then next step will be formulation of mathematical model. Here if you see, whatever problem is been given, I have to analyze it. If I want to analyze it from the problem, that is from the hardcore problem, I have to convert it into some model. Usually we convert it into some mathematical model, because it has been observed that mathematical models are very easy to analyze. Therefore, once we are getting the problem, we will formulate the corresponding mathematical model corresponding to that. This will be your second step. The third step is deriving the solution of the model. Now, what technique or what methods you will find to solve the mathematical model? For that, I have to find out this one, deriving the solution of the model, and optimization comes into picture basically at this stage. Optimization is the technique by which you can find out the solution of some mathematical model. And the last step is, not last step, the validation of the model. Means you have to test the model whether it is giving proper result or not. If required, you have to improve it and improve your technique so that you can obtain the better result. So, this is the next part is validation, and the last part will be implementation. Implementation comes into picture because whenever you will talk about the various models, in that case number of variables, number of constraints can be many. Many means I may have to find out an problem where I may have 100 variables, I may have 200 equations, and which is not possible to make hand calculation. So, I have to use certain techniques and I have to computerize it, I have to write down certain algorithms. So, for that part our implementation comes into picture. So, the general form of LPP, if I have to tell, general form of linear programming problem, it is, I am writing maximize, it can be minimize also, I will come to that, maximize or minimize, z equals C1 x1 plus C2 x2 plus Cn xn, subject to A11 x1 plus A12 x2 plus A1n xn, which is less than equals B1, A21 x1 plus A22 x2 like this way plus A2n xn less than equals B2, and AM1 x1 plus AM2 x2 like this way plus AMn xn less than equals Bm, and this we call as the resource constraint, and please note this one, the decision variables should be x1, x2, xn greater than equals 0, which we call as non-negativity constraint. So, In an LPP, please note that the decision variables with which we want to work all must be non-negative, and we have to optimize the function. It can be maximize or minimize the function. Z equals C1 x1 plus C2 x2 plus Cn xn, subject to satisfying certain constraints. And please note that linear programming problem means from the name itself it is clear the objective function as well as the constraints will be linear in nature. The variables will be only non-negative, it may be discrete, it may be continuous. So, if I have to write down in the compact form, I will say maximize Z equals summation j equals 1 to n Cj xj subject to summation j equals 1 to n Aij xj less than equals Bi, where I equals 1 to m and xj greater than equals 0 for all j equals 1 to n. So, this is in compact form. Maximize z equals summation j equals 1 to n Cj xj subject to summation j equals 1 to n Aij xj less than equals Bi and xj greater than equals 0. This again we can write it in the matrix notation also, which becomes much easier to represent. Maximize z equals, we are writing it as C into x subject to Ax less than equals B and x greater than equals 0, where C, x, A, B all are the column vectors. I can represent it from there. And if I have to minimize the problem, then in place of maximize, here it will come minimize the function, but sometimes what we do in general cases, we write down minimize z equals Cx subject to Ax greater than equals B and x greater than equals 0. So, basically if you see for minimization, the constant we are taking greater than equals, and for this one we are taking the constant as less than equals. If you see in LPP, then basically you have m variables, because here if you see we are having m equations and n variables. I have to find out the solution of these n variables, which will be written, which will satisfy the constraints. So, in standard form we can write down two things. I am just writing standard form, and also in standard form if I have to write down, I am writing minimize j equals 1 to n Cj xj subject to j equals 1 to n Axj equals Bi. I will take values like this and xj greater than equals 0. So, minimize j equals 1 to n Cj xj subject to Aij xj equals Bi. In standard form we are, means whenever I will convert it, I may have inequality, but before solution I have to transform it into the equality, and here I am writing the canonical form. In canonical form its minimization I am just writing, not the maximization. Cj xj subject to j equals 1 to n Aij xj, which will be greater than equals Bi. Again I will take the values 1 to B, will take 1 to m, and xj greater than equals 0. So, here in general canonical form means what, whenever I will formulate the problem, the constant will be maybe equality, maybe inequality, it will be greater than equals or less than equals depending upon I am minimizing or maximizing the problem. But whenever I am trying to find out the solution, then the inequality I have to convert it into equality, and then we will find out the solutions. So, next we will see in the next class what kind of assumptions we have used to find the solution of LPP, and then we will go for the graphical solution and other things.